As we end chapter 4, we're going to be as we end chapter 2, we're going to be looking at graphical misrepresentations of data. This is really key. It's always said that statistics, the only science that enables different experts using the same figures to draw different conclusions. Well, this is true not only in the figures, but also in the data and how it's reported or how it's interpreted. But the graphical representations, etc., are really key. And so raw data is important, and being able to evaluate what graphs are saying, what tables are saying, with a critical mindset is key. And it's hard because often when we see something, I think we almost accept it as true when it looks like a data-driven graph, or it looks like a data-given opinion. Okay, so it's really important to be able to look at things critically and to evaluate them and step back and say, is there anything wrong with this? And so we're going to start with an example. Example 1. A home security company located in Minneapolis develops a summer campaign with the slogan, when you leave for vacations, burglars leave for work. According to the city of Minneapolis, roughly 20% of home burglaries occur during the peak vacation months of July and August. The advertisement contains the graphics shown down here on the left. Explain what is wrong with the graphic. So take a minute or two and see if you can figure out what's wrong with this graphic. Okay, hit pause, and when you're ready to continue, hit play again and see if you got it right. Think of it like a little puzzle. So look at this. What could possibly be wrong here? July and August, 20%. All the other months, 8%. So consider how the categories of data are defined. When we're talking about this is a relative frequency bar graph. How do I know that? Because it has percents, right? Well, relative frequency bar graphs have to add up to 100%, or a sum of 1 if we're doing decimals, okay? Well, notice here, these don't add up to 100%. They only add up to 28%. So what's wrong here? Well, if we do the calculation, we can see that what's being reported for the other months is the average per month, versus what's being shown for July and August represents the combination of both months together. So anyone looking at this would assume that, oh wow, burglaries are more than double in July and August. But this is incorrect, because what we're again showing there is the sum of 2 months, which if you just took them in half is only 10% each. So it's not really a great uptick in burglary. And probably warmer weather makes burglaries easier. Here would be a more accurate display of the data in this problem. Here we can see that the increase during the month of July is not as dramatic as the bar graph that we saw before. And August actually has fewer burglaries than September or October. So we can see this is definitely misleading. And it might even be considered deceitful, because the security company is intentionally trying to convince consumers that July and August are much higher burglary months. So let's look at another example of misrepresentation of data. A national news organization developed the graphic shown in the bottom left to illustrate the change in the highest marginal tax rate effective January 1st, 2018. It's a comparison between 2017 and 2018. Hit the pause button and look at this and see if you can figure out why this graph might be considered misleading. Once you're ready, hit play again and let's go forward. Well, when I look at this graph, it looks like the change between 2017 and 2018 is more than 3 times less, right? So the highest income people are paying the lowest income rate, and it looks like it dropped by, you know, by more than 3 times over that period. But if you notice, the difference is actually only 2.6 percent points. When I add the actual values for 2017 and 2018 into the graph, we get a much different perspective or perspective of the change. The visual makes us think that it's a change of over 3 times, when in fact it's just a drop of 2.6 percent points. And the reason is that the graph starts at 36% versus starting at 0. And so if you see this graph, in this graph, the decrease is still apparent, but the distortion due to perspective of the size of the decrease is taken away. So here you still see that it's dropped, but you don't get the impact that it's dropped by a factor of 3, if you will. Now let's look at another example. Here we have a time series graph in the figure, which depicts the number of residents in the United States living in poverty. Why might this graph be considered misrepresentative? Again, hit pause, look through the graph, and see if you can figure this out. Again, we have a very similar problem to what we saw before, in that this graph may mislead readers to believe that the number in poverty has more than doubled from 2007 to 2014, as you can see from here, to 2014. If we look at the graph closely, once again we notice that the vertical axis begins at 30,000 instead of 0. Now, this type of scaling is actually quite common when the smallest observed data value is rather large number. Notice that this is actually numbers in thousands. It's not necessarily done intentionally to confuse or mislead the reader. Often the main purpose in graphs is, particularly time series graphs, is to discover a trend rather than the actual differences in the data. And we can see here quite easily that the trend was increasing between 2007 to 2014, and then it starts decreasing again. What the author should have done here is indicate clearly that the graph does not begin at 0 by including this little squiggly symbol in the vertical scale that you can see here in the other, in an actual graph. And again, it's very subtle, but it's an important difference so that we don't make visual misinterpretations, or if we do, at least the author shouldn't be blamed, because he's made it clear in the second graph that we're not beginning at 0, that we're skipping a whole trend because most of the data is in a higher part of the graph. Notice here we have a different type of graph which gives us a better representation of the data. This is the same data that we've been looking at, specifically the percentage of U.S. residents living in poverty. But the lack of bars allows us to focus more on the trend in the data rather than the relative size or area of the bars. So again, even in this graph, if you'll notice, we still have an axis that's not beginning at 0, or at least we're skipping a lot of the earlier parts of the data, but we're still seeing, without the bars, we're focusing more on the trend than the relative size and the relative change between that looks visually much larger. Let's look at another example. The bar graph illustrated in the figure is a USA Today type graph. A survey was conducted by Impulse Research for Quilted Northern Confidential, in which individuals were asked how they would flush a toilet when the facilities are not sanitary. So we have 41% use shoes, 30% you act just like they would at home, and 17% use a paper towel. So what's wrong with the graphic? Again, hit pause, look it over and see if you could come up with what could possibly be wrong here. So first, it's unclear whether the bars are just the toilet paper or they actually include the roll of toilet paper at the bottom of each one. In either case, the roll corresponding to used shoes, 41%, should be 2.4 times as much as the one for paper towel, because 41 divided by 17 is 2.4. So this bar, the first one, should be 2.5 times almost as much as the last bar. If we include the toilet paper bar, then the bar corresponding to used shoes is less than double. If we don't use it, the bar corresponding to used shoes is just double, but certainly not 2.4 times as much. So in all of these cases, the vertical scaling is incorrect. What's interesting here is that while the other graphs that we saw about vertical scaling overestimated the difference between, this graph actually underestimates the difference between the lowest answer and the highest answer. And so you kind of wonder what's going on here. And it's really good, it's good practice, as we saw in the last few examples, that you want if you're going to use a bar graph, that you want it to tell a story, but you don't want it to misrepresent the story. You want your graphs to at least be accurate, and if you're not starting at the same place, then you need to indicate that, as we saw in the last example. Our next example, I think it's pretty clear, but let's see how you think about it. Soccer seems to be losing popularity as a sport in the US. In 2010, there were approximately 14 million participants. By 2017, this number dropped to 12 million. To illustrate this decrease, we could create a graphic like the one shown in the figure below. Describe how the graph may be misleading. Hit pause, and then when you're ready, come back. Well, to me, it's readily apparent that the drop looks more, it's a 2 million drop, which is a lot of people, but relative to the overall populations, we're only talking about 1/7, or what's that, about 12, 14% change or drop in participation, whereas this ball is like 1/4 of the size. So that's the very first thing that happens, is that visually our brain interprets visual data really quickly and makes some judgments on this. So if we saw this graphic embedded in some kind of article about soccer participation dropping, I would immediately think that it's just a fraction of the size in those 7 years. In 2017, it's just a fraction of the population, a much smaller fraction than it actually is. And yet the graph on the left has a size, an area that's 4 times the size of 2017, which is a much larger drop. While the number of participants, the raw data, is given to us in the problem, imagine if this was an article. That information would probably be included in the article, but it could be embedded deep in there and more difficult to find than just in a short paragraph like this. And so as people are reading, they probably would read the headline, "Soccer participation drops drastically," which is what we know media does. They want to get your attention, so they always use adjectives that are hyperbolous. You see this all the time when they talk about Wall Street numbers dropping. Drastic change, the Wall Street Dow rate plummeted. But if you look at the percentage rate, it may have only gone down 1%, which in my mind, anything changing by 1% is not a plummet. So there was a 14% decrease in participation from 2010 to 2017, not more than the 300% as indicated by the graph. So to be correct, we should probably use balls that are relative, the area of each ball is relative to the raw data, 12 and 14 million. At the bare minimum, we should put the raw data on this graphic so that it's less misleading, if you will. Probably a better way to do this graph, another picture graph, would be to do a graphic like the one that you're seeing on the screen. A smaller picture repeatedly with each picture representing a certain quantity. As you see here, each soccer ball represents 1 million participants, and now you can see a better relationship between 2010 and 2017 that's much more accurate and much more supportive of the raw data and doesn't make people make faulty judgments, faulty conclusions about this data that the graphic on the left did. So let's look at our last example. Again, another misrepresentation. The figure represents the educational attainment level of education in 2017 of adults 25 and older who are U.S. residents. Why do you think this graph might be misrepresentative? Again, hit pause and see if you can figure that out. It's a little bit hard for me to read with the colors, etc. But notice that the way that a three-dimensional pie chart tends to overstate the significance or the size of things that are closer to the reader. For example, in this graph, the category graduate or professional degrees looks about the same size as the category high school diploma, which is right over here, okay? Yet in the raw data that we saw previously in previous examples, there are 27 million individuals who have a graduate or professional degree and 60 million who have a high school diploma. You know, this is a difference of almost well over double, but it doesn't necessarily look that because of the way the three dimension, the parts that are closer to you seems bigger. So notice what happens if we just rotate this image to bring the category some college no degree to the front. We obtain the graph shown in the new figure. Now some college to no degree appears to be the largest piece of the pie, which is also inaccurate. Clearly, the three-dimensional representation distorts the number of individuals in each category, so these types of graphs should be avoided. It's interesting because I used these a lot in marketing presentations before, just because I thought they were a cooler representation of the pie, and I wasn't aware that, you know, if things were relative, that the relative size of things were going to be distorted by that three-dimensional representation. And so when you're doing a pie chart, avoid the fancy three dimensions and the pieces like that because it can distort the data. And you know, I use this in Excel to create graphs many times, and almost every time I used a pie chart, I would use something like these three dimensions, not recognizing that I was in some form skewing the raw data, at least in people's interpretations of the conclusions made by the graph. So we've seen a lot of examples of bad graphs and some ways to clean them up. So what are some guidelines for constructing good graphics? Title and label the axes clearly, providing explanations if needed. Include units of measurement and a data source when appropriate. Avoid distortion. Never lie about the data. Never lie about the data. Unfortunately, this is what a lot of folks do, specifically and intentionally using graphics, not explicitly lying, but implicitly lying by using graphics that give people the wrong impression than what the raw data would. Minimize the amount of white space in the graph. Use the available space to let the data stand out. If you truncate the scales, clearly indicate this to the reader. We saw that with the vertical scale specifically and especially. Avoid clutter, such as excessive grid lines and unnecessary backgrounds or pictures. Don't distract the reader from the data. Avoid three dimensions. The three-dimensional charts may look nice, but they distract the reader and often lead to misrepresentation of the graphic. Do not use more than one design in the same graphic. Sometimes graphs use a different design in one portion of the graph to draw attention to the area. Don't try to force the reader to any specific part of the graph. Let the data speak for itself. Avoid relative graphs that are devoid of data or scales. These are some great tips for you, and this is the end of Chapter 2.